Yeah. Then come back. Let me make a couple of announcements. After this talk, there will be a photo. So please don't run away. It's outside, I guess, or
it's on the stairs.
On the stairs here. Then we decided, so David Reuter, unfortunately for private reasons, has to cancel his talk. Francesco agreed that he gives his talk not in the afternoon, but in the morning. So there's a shift in the program. And then the first talk in the afternoon will be earlier. So those who want to leave a bit earlier to Paris to have a walk in Paris before going to the Bateau Rouge, will also to the restaurant and the food, they have a chance to go a bit earlier to Paris if you want. Okay. And then any more announcements? Okay, not then I should.
Will we have like a group of people who go here? Maybe we can do that later.
Yeah, we can arrange this later, whether you are interested to go in a group to Paris after the last talk. We can arrange this over coffee and announce it. Yeah. Okay. And then it's a pleasure to announce Ingo's last talk. Yeah, I will.
Okay, thanks for coming back. That's the last talk. So what what did we do in the first two talks? In the first talk and a bit, we discussed chiral conformal field theory, which we wanted to think of as a three-dimensional quantum field theory defined on which are topological in the interior of the three manifold and holomorphic, depend holomorphically on things on the boundary. Then we decided that we can turn this into a purely topological theory by cutting off the conformal boundary, and we understood this manifold which had a conformal boundary and the parameterized topological boundary as we could think of this as a map between topological functors. Then in the second lecture, we tried to see how can we use the chiral conformal field theory to build a full conformal field theory, which is single-valued and compatible with factorization on two-dimensional surfaces with a conformal structure. We said, well, let's try and phrase these consistency conditions in terms of the topological field theory, which is part of the chiral theory. And that led us to this definition, which is the last thing we did yesterday, which is now phrased purely in terms of topological field theory. So that notion makes sense whether or not you have an underlying MUA or not. So, so a consistent system of correlators, you fix two modular fusion categories, C and D, and you need to point at two pieces of data. One is an object, and C product with D reversed braiding and twist. And the other is a collection of elements in the state spaces, the topological, so a collection of elements parameterized by topological surfaces with marked points, local coordinates, and a plus minus sign. And each of these is an element in the vector space which the 3D TFT assigns to the doubled surface. What was the doubled surface? That was just a copy of the surface and its orientation reversed version, disjoint union. You keep all the marked points, and sort of the pairs of points which are sort of the same on sigma and minus sigma, you will label by this object F which you've chosen, right? Or if the sign is plus or if the sign is minus, you label it with the pure, right? And then you agree that you evaluate for this disjoint component, you evaluate the TFT for C, and down here you use the TFT for D. You can think of it as a topological field theory which can operate on three manifolds where the three-dimensional regions are colored by different modular categories. But in this instance, they don't touch. So we can just say evaluate this with the TFT for C and that with the TFT for D. So you get the standard product of state spaces. So this encodes the idea that a correlator of a surface should be an element in the space of blocks of the Schottky double. Then this collection of elements has to satisfy two consistency conditions. One is compatibility with the mapping class groupoid, which means that if you have an isomorphism between two of the surfaces compatible with the marking, then you can build you can look at the mapping cone over one of these surfaces. You take its doubles, then you have the mapping cone over the disjoint union. You evaluate the TFT on this mapping cone, and it should transport the vector for the surface sigma to the vector for the surface sigma prime.
Mapping cylinder.
Mapping cylinder. What did I say?
Mapping cone.
Oh, that also sounds good. But yeah, mapping cylinder is what I wanted to say. Thank you. Mapping cone. Not mapping cylinder. No. No, mapping cone. No. Yeah. Anyway, the thing which is correct. So, and then there is a second consistency condition, which is sewing. So you point you in your surface. You point at a point which is marked plus and another point which is marked minus, and you construct out of this a new surface using the parametrization, which where you sort of cut out little circles around these 2 points and you glue them together. Right? So the 2 points get removed, and you've glued in sort of a tunnel here. And we last time had a 3-manifold which implements this gluing. You again take its double, and you say that if you apply this gluing 3-manifold to the vector for the surface sigma, you get the vector for the glued surface. Okay, that's it. So these are my 2 consistency conditions. And so if I can solve them, then I say I found a consistent system of correlators. And if you want actual CFT correlators, you have to take this solution and you have to glue the conformal boundary back on. That's it. And now what I want to do today is I want to present one solution to this. And then I want to explain how you can obtain the general solutions, how you can classify solutions to this question. And so the one solution I want to present before we talk about how one can maybe classify them is the diagonal closed CFT. Closed means that I don't yet allow boundary components. I might get to that at the end, but for now we do not. So diagonal, in the situation for diagonal CFT is that these 2 categories C and D are equal, that I make the following choice for my object F, so the space of bulk fields if you want. So I sum over irreducibles and I do U dual. So that's the, you cannot think of that as an end or a co-end in a category, doesn't make a difference in the semi-simple setting. So that now lives in C box C reversed. So that's one of my pieces of data. And I want to later again stick to the easing example. So if C is the easing modular category, well then that obviously is simply the object 1 box 1 plus sigma box sigma dual plus box epsilon. Right, so that you may recognize just as a state space for the easing CFT. Okay, so now we need to come up with the more complicated piece of data, this infinite collection of vectors, one for every surface. And so the idea to have here is that so far we have described everything so very intrinsically via topological field theory. And so let's try and continue to do this and also try and describe these vectors somehow by topological field theory. Right, and so how could that work? Well, we want to generate a vector in a state space of a TFT, and that can be done if you somehow find a bordism which goes from empty to the double of sigma. So I want to present a cleverly chosen family of bordisms from empty to the double of sigma. And then I want to show that for this choice, these 2 conditions hold. So what's my clever choice? That's something called the connecting manifold. For my surface sigma, remember, so sigma is an oriented compact surface, and with the underline I meant is that it has this marking. And so what is the connecting manifold? As a manifold, I call it M sigma. It is simply you take the surface and you multiply it by an interval. For some reason I want to have that interval -1, 1. And I want to think of this as a bordism which goes from empty to the double. Right, and that makes sense because this has two disjoint boundaries. One is sigma, and the other one is sigma orientation reversed. So really, you think of this as the manifold which sits in between these two sides in the little picture I drew here. So let me draw that picture again. For example, so let's take our surface to be maybe like a sphere with 3 marked points, and let's say we have P1 plus, P2 plus, and P3 minus. Then for the connecting manifold, I am asked to take this times the interval. So I will draw it like this. Right? So it's like a 3-ball with a 3-ball removed. So that's the sphere times an interval. And now I have to, so it's a little bit annoying in notation that sort of here I label my points by this direct sum, so I'm implicitly linearizing. So I have to do the same thing here. So let me first pick, right, so over each of these points, I get now one of my my ribbons in the 3 manifold. Okay, so this is the boundary sigma, and that's the boundary minus sigma. I want the ribbons to always point into the manifold for some reason. So they all point in, and then I label this one by U1, this one by U1 dual, and so on, U2 dual. Well, except for if the sign is minus, then I want to have them both point outward, and so I have U3 dual 3. And so this I want to call M sigma and then U1 U3, or if you have a more complicated surface, then this goes from U1 UN, how many punctures you have. And so I have to say what is this what is the morphism with which I want to join these two objects? But here I can just choose the evaluation because I'm picking a morphism from U dual to the identity. Here I can choose the co-evaluation, but that doesn't quite work. So the actual thing I have to choose for ribbons which point outward is the dimension of U3 divided by the square root of the total dimension of the category C, and then times the co-evaluation. So that's the connecting manifold. And now I can make the definitions. I can make an ansatz, which I then have to verify that I take my collection of vectors to simply be, right, I apply Z to, I apply the TFT for C to the bordism, which goes from empty to the double of the surface given by, that is M sigma. And I'm thinking of this as being the linearized version of this, where I direct sum over the U components as dictated by the object F. Let me sort of write this as linearized. So linearize over direct sums, or linearly extend if you want. Okay, so that's my ansatz. Does the ansatz make sense? Are there questions or comments?
Well, why need this normalization?
Yes, it'll be related to an exercise I will give in a moment, and you will see where this exercise. Yes, so yeah, do the exercise, which I will soon say what it is, and then you will see the normalization. More comments or questions. So at the moment it's a bit weird. Why would I need to do this? But we will see. Okay, and so now I want to make a proposition. And the proposition is that this choice of F and this choice of gamma is a consistent system of correlators. And so I therefore have to prove property 1 and 2. And for property 2, I've already drawn some pictures. So for property 1, that's an exercise. This exercise doesn't need the normalization. So that's not so hard to see. So let's just do one example. So what's the typical, so in this, what could be a mapping class group element? It could be that you sort of continue this point, one point around another point. So you'd like to a braid group move. If you look at what that would mean here, what the mapping cylinder would do, it would take both ends and move them together around the other point. So at the end, you end up precisely with the same three manifold, right? And so that's how it works in general. The mapping cylinder you glue up here and you glue down here, you can find a diffeomorphism of the resulting three manifold to the configuration which didn't have the two mapping cylinders applied. So that's how you show this. And then for two, we have to verify this identity. And so that's right, I do this the right way around. Certainly not. So the this is L, which was supposed to stand for left hand side and right hand side. That's the wrong way around. So let's try and see what in this example the two sides produce. Will require a bit of imagination. So I'm drawing two patches of my surface sigma. One where there was a point here and a point here, which I want to glue together. Right, so it tells me take what my ansatz for gamma. My ansatz for gamma I've drawn here. So right, so whenever there was a marked point, there's a stretch of maybe I'll just do this. So wherever there was a marked point, there's a stretch of U ribbon between them. Then I'm asked to glue on the bordism, which implements the gluing. But now, you have to do this for the top copy of the surface and for the bottom copy of the surface. So you glue on this handle on the top and pass the U ribbon through it, and you glue in this handle on the bottom and pass the U ribbon through it. And outside you don't change anything, right? And now for one of them, for this one, I've got this funny normalization factor. And I have to sum over U, because that's to be done for the whole state space F, where the sum over U comes from. And outside of these two patches, I don't change anything. So that's this picture, the picture for this side. And what do I get for the other side? I have to evaluate my prescription gamma for the glued surface. But in the glued surface, there are no more these two punctures. Instead, they are replaced by a tunnel where I've glued the surface together. And so what I get is I just have this tunnel times an interval. So it looks like this. Does that work in your head?
Can you repeat?
So what I'm doing here is I'm saying, so I had a patch on my 2D surface, and right. So I had my 2 points, and I glue these together. So I erase the points, and I glue in a little tunnel. And then to get to the connecting manifold, I have to take this picture times -1, 1. And so that's what I've tried to draw here. It's like this tunnel times like a fattened tunnel. And so these don't look the same. So that's a bit disappointing. But exercise, that's the exercise. These are actually equal by sewing. By surgery, I should probably say. So I claim, so that's the reason for normalization. Then this sum is precisely the surgery color in Richtig and Torayev theory. And I claim that if you work out what is the new 3 manifold which that represents, you get this. This exercise is actually not that easy if you haven't seen that before. So maybe I put a little stuff and I give you a little hint. The hint is to work with cake pictures. So here's my favorite picture of a 2 torus, and I now want to have a favorite picture of a solid 3 torus, which is a little slice of cake. So this is the boundary, and that side is identified as 1, and I claim the surgery relation can be written as follows. So I have some prefactors, sum over simples, and I have the same boundary. I do nothing to the boundary. But then I glue in my piece of cake the other way around. And I put a U ribbon in. I claim that's the surgery relation. And I claim if you use that relation with that, and you draw it all as nice pieces of cake, then you can see it. But it's not that easy. And if you don't manage and you want to manage, ask Aaron. He has done that. Hey, no. Okay. Are there questions or comments?
I have one question. So if I take a closed surface, no boundary components, then you have that surface and you have the orientation reverse one. So you have the state space and you have the dual, which is that.
Oh, and so whatever. So there's a pairing between these, yes?
Yes, and this would be identified with the endomorphism. And then here, for this example that you have, does this select the identity in that endomorphism?
So if you would indeed do the identification of the state space for minus the surface with the dual, using the canonical pairing you have, then I think that turns that into the identity map.
But it's not so easy to see with what you're doing.
Well, but you know, so it's you have to sort of maybe implement how you think of reverse orientation of some of these ribbons. So I think it's just getting confused with convention. So, so if you translate conventions correctly, that'll be the identity map on the space.
But you say it's true. In the Cardi case, it's true.
And so then it makes part one even easier to see because we're saying that the identity commutes with the mapping class group.
Yes, because I acts through algebra maps.
There were comments or questions. Then I want to do something. Erase this. And I want to do the easing 4-point function in this language to see what we get.
Sorry, in terms of this identity perspective, does that dimension come up from like the pivotal structure?
But that's vague enough to say yes. So you have to, right? So you would have to work out the pairing, right? So if you set it up this way with abelation and correlation, maybe it's not so surprising to see some dimension factors somewhere. But then to have a basis, dual basis, you somehow have to get rid of this. Then it's sort of maybe more mysterious where the square root dimension C comes from, but that comes from the fact that the empty 3-sphere in Richtig Interaev evaluates to that. And so this is a normalization which just pops up in places. So let's try and put this together and understand something about this 4-point function we had in the very beginning. So I'm thinking of this as a 4-point function of the easing 2-dimensional conformal field theory on the complex plane, and that was this norm of F plus norm of F minus. And now I want to use this formalism to see how can I recover this expression. So we would first now say that how is that written in terms of 3D TFT? So it would be a correlator for having a conformal boundary and another conformal boundary. So this altogether is the Schottky double of just the surface we started from. So maybe we have one complex plane here, orientation reverse complex plane down here. And so I have one, and so now we are tasked. So now I want to fill in this diagonal solution. So I want to say what do I put in this? I want to put in the connecting manifold between these two places. So I get these ribbons here, right? So this would connect the point Z to the point Z bar in the double. Okay, here I have my funny convention with the sigma dual, and so on. Maybe there's a point 1 here. These ribbons are all called sigma, and then out here somewhere there's the point infinity, and again I connect it with the sigma ribbon now pointing outwards, and I have this normalization factor dim sigma over square root of dim c. So in easing, what is this? This is square root of 2. This dim sigma is 4, and so you can work out what that number is if you want to. And so I want to compute the correlator, which I've written there. And how can we do this? So what we really want to do is we want to express somehow this in terms of standard conformal blocks for these two copies of the complex plane. So I will first turn it into a topological question to ask. So I cut off the conformal boundary. Then we do a little topological side calculation, which is that now we have this topological boundary here and here. And I've got this picture. So let me not draw in all the details again. And so now that, if I apply the TFT to that, so that the Richtig integral theory for the easing modular fusion category, then that generates a vector in the state space for the 4-punctured sphere, tensor the state space for the 4-punctured sphere. But I know a basis of that state space, and I want to express it in my preferred basis. And my preferred basis is that I think of the sphere as the boundary of the 3-mole, right? And that I draw my preferred ribbon graph. And that's my preferred basis. So we have sigma, 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 sigma. And then here we can have another object alpha, and alpha lives in either 1 or epsilon. So this state space in the easing theory is 2-dimensional, right? And that's the basis. And then the same holds down here. So I again do my favorite basis. So again, that's the 3-ball with this boundary. And I do the same picture. Now here I put the beta, but again, beta also in the same set. And here I have my sigma duals. But sigma dual in easing is the same, it's isomorphic to sigma. But okay, never mind. So we do this. And now it must be true that this vector, whatever it is, can be written as the linear combination of those vectors because these give a basis. So there have to be some coefficients, C alpha beta, which make this true. Right, just by basis. And that's an exercise. Check. Let's see, alpha beta is actually delta alpha beta. It's just 1 or 0 with these normalizations, and it picks out the terms where these two indices are. Okay, so that's a TFT computation one can do. But then I stick that back in here after having cut out this bit, and I know in TFT it's the same as that bit. I can glue that back in, and so I learn that that is actually equal to having this surface again with a 3-ball, and then this picture in here. So it's the sum just now over alpha, which goes 1 epsilon. And here is alpha, and then down here I've got the same picture with the complex with the conjugate plane, and again I have a 3-ball. This is boundary, and this graph again is alpha. So the legs are all called sigma as before. I didn't touch the outer legs. And so this picture would be your preferred picture for the standard conformal block on for the standard 4-point block on the sphere, right? Where if you bring these 2 points together, there's a well-defined singular behavior, and the intermediate channel is given by this alpha. That's the, yeah.
Is pairing as a number or a just the these brackets that you have? I'm expecting it to be a number, but
My bracket is my notation for correlator. It's a thing which assigns a number to this. Oh, I should say all these points are labeled, so I always pick the highest weight in each.
Okay.
Sorry, in each representation. I forgot. I have to put that, otherwise the function, yeah, sorry. Okay, so again here also, and then this conformal block with this marking is what I've written is either F plus or F minus, right? So this is for alpha as 1, this is for alpha as epsilon, and the same down here. So therefore we get precisely this formula which we had when we started out. So that would be the TFT computation which produces that formula. And it also yes. Okay. So now it's precisely the formula we started out with. When we reproduce it. Okay. So that's what I wanted to say about the diagonal solution. There are comments for yes.
So do I understand correctly that to get this number, I do need this blocks to conformal blocks to topological blocks identification for this last bit?
Yeah.
Okay.
I mean,
in some sense, it's a guess, right? Like writing actual functions on Z.
So
in general, like I would need identification.
so the identification, as I said, to make that in general work in the way I presented it here, needs an additional piece of mathematics. In the sphere, I can just make it precise for you anyway, right? So I can write a composition of intertwining operators which precisely corresponds to this and which will be correctly under sewing and monodrophy. So I think on the sphere you can just write down how that works. But it's just in general.
Sorry, the structural constant is encoded inside F minus, for example.
Oh, you are disappointed that you don't see the structure constant.
The 1/4 or something like that.
Now, F plus goes as follows. F minus goes like exercise C sigma sigma. Right.
But it is a topological, you get this 1/2 from a topological information,
So
where it is the origin of this 1/2.
So what's going on here? So to get the actual structure constants, you have to be very careful how you normalize your things. So you have to pick your standard normalization of blocks, which I did not do in my example because I didn't want these constants. But if you pick the standard normalization of blocks, then the constant would have been sitting out here, and it would have been, and you would have been able to compute it from the TFT. So if you set up your normalization of these vertices in such a way, which is not trivial, to correspond to some standard normalization of conformal blocks, then the TFT does compute for you the structure constants. It does. But if you actually do it, you will there's so many little details, but it works.
Sorry, it comes from the topological.
So these numbers, the TFT can compute for you these numbers.
So who is Z at all in the topological setting?
Sorry, what?
Who is this Z in topological setting?
The Z.
No, Z is the point. No, the
Right,
point
now
we don't see.
You have your second.
And now I put the conformal boundary, right? And so then on the conformal boundary, it makes sense to say.
Absolutely, but in
What is it?
topological setting, who is
And-
Z?
And the topological setting. So now I would have to explain a little bit, how do I go from the topological boundary to the conformal boundary?
You
And so I would have said,
secretly you have this.
I know what conformal block this has to be. And then I would maybe think of this as 0.0 Z1 infinity. I'd all line them up on the real line. Then I'd have a preferred way of thinking of this as a function here, and if I do on the conformal boundary, and then I would continue this from that point. So
is it correct to say that you have a linear map from the basis from the vector space, the TQFT vector space of the sphere,
Yeah.
to a set of holomorphic functions on the moduli space?
yes,
And
but that's
what
part
you
of the
call-
data, right? So if I say
Such that it
talk
can
about
use this mapping onto factions.
I talk about the easing theory, I have.
Properties you can see.
So this is an additional datum you
Yeah.
require.
So if I want to talk about conformal field theory correlators as actual functions, I need to know what VOA I started from. to be able to talk about the conformal blocks as functions.
Okay.
So, and I need to have the explicit identification of the TFT state space with the corresponding conformal block spaces, which is a comparison of modular functors. And the intuitive way to think of these, which hopefully can be made into mass, is to cut off the conformal boundary, and this bit of the surface gives you the map from TFT state spaces to the conformal blocks.
And do I get correctly your answer before? For the sphere case, you can explicitly produce these functions as functions on the configuration space of endpoints.
Yeah, if you hand me this,
Given the VOA.
Yeah.
For general VOAs.
like for rational.
Rational, minimum models.
So- So this, I mean, this you can probably do significantly more generally if you're just on the sphere, but so certainly, well, what?
C2 finite. You mean
C2 finite would also work for this, I guess. You'd have to be a bit careful what you mean by F then.
No, I mean, but you need a finite number of simples in general for rational.
So
No?
I believe there's potential for generalization, which has not been done. So this works to some extent for C2 cofinite, but not semi-simple. But I just want to sit on the strongly rational case, so I don't have to worry.
As you know, the origin of the structure constant with topological. This because we know in the minimal model there is like there are always of the form that are given by gamma function, the simplest one. No, do you think that the topological theory can produce some other structure constant which are not given by gamma function?
So where do the gamma functions come from? So if you work out how to, so if you work out the normalization of the conformal blocks for the minimal models and you do this F matrix move, then there is a gamma function in there, right? And so, but the gamma function is a normalization. So you can normalize blocks differently and all the gamma functions go away. So you just,
Not for all the conformal blocks.
you can normalize your intertwining operators so that there are no more gamma functions if you want to. And then you have a nice life without gamma functions, but it's harder to see what the actual structure constants are, or you put them in, that amounts to specific normalization of these preferred bases, which couple two representations to a third. So maybe we talk about this later. It's a question of how you normalize your standard basis in the TFT.
But you have preferred normalization.
Sorry?
Yeah, preferred normalization.
Well, you have a preferred normalization for minimal models where you say I take the leading singularity with coefficient 1. Right? But in WZW models, that's not true because it's not like the highest weight vector. If you take their OPE, they don't couple to the highest weight vector anymore. They go to some other vector in the representation. So yeah, there's not a canonical normalization in that sense.
I mean, I think you have this. Okay, we can discuss later.
Let's instead talk about more generals. Very briefly talk about more general solutions, because I do want to also talk about the easing model with a boundary. I need to get towards me. Solutions. Please. So I want to have just two sections, more solutions, boundaries. So maybe with this we say correlators.
But without boundaries, there is no more solutions than diagonal.
So these are two separate statements.
Yeah,
One
yeah.
can talk about the theory with boundaries, and one can put more solutions, and one have more solutions with boundaries. So this is not typical. So for easing, it's actually all solutions, and in a way I can point at.
Diagonal? Oh, no.
But well, let me just say, and then if it's not so clear, just ask correlators from surface defects. Suppose now you're in this situation where maybe even C and D are different, and you were happy with this idea that we can get this solution for gammas out of the setting up the 3-manifold in a clever way. So you try to do the same thing again, and you say, well, maybe here we have a bit of, so maybe this is a bit of the surface sigma, and down here there's a bit of the surface minus sigma, maybe there's some marked point. But now you have a problem because up here you should evaluate using the TFT C, and down here you should evaluate using the TFT D. Right, so again, this is my connecting manifold. I want to build a connecting manifold, which is sigma times -1, 1. And here, if I call this coordinate T, here I've got T is 1, here is T is -1. And so, you know, what it does is fit together. And so clearly what you want to do is to put an interface, a 2-dimensional interface between the TFT for D and the TFT for C. And you want to maybe put this maybe at the height T is 0. So you get a copy of the surface at height T is 0. And you want to somehow label this by, let me call it curl M. This should be an interface, topological interface. Topological, I just call it a surface defect, which on one side has a TFT for C, and on the other side has a TFT for D. And these ribbons somehow should cross this at some point junction alpha. So that could be an idea you have, but then you have to say, well, now I have to develop a little bit the theory of 3-dimensional TFTs where different 3-dimensional parts are labeled by different modular categories, and I need some way of understanding how can I label different surface defects which sit in between this. So I just drop some names. So this sort of TFT was looked at in a joint work with Vincent Koppen, Vincentas Molivicius, myself, and Christoph Schweigert. So we developed this TFT to some extent. And so this would give you a functor out of stratified Bordisms into vector spaces. And the stratified strata are decorated so that 3 strata would be decorated by modular category C. Then
The same C on both sides?
but now I have C and D.
C and D. Oh, I didn't. Okay.
B is not C reversed.
D is more general. D is another modular fusion category, right?
At the
Never
moment, I
saw
will constrain it a little
Not
bit.
related to C. Yeah.
Constrain it a little bit in a moment. Okay, what was your question? Point, comment?
That D never saw C at this point.
So again, so yes, indeed. So the so we were thinking of so that would be rep V, where V is the holomorphic fields, and that's rep W, where W, the VOA, encodes the anti-holomorphic symmetry of your
So you
series.
are still in that picture here or no?
Sorry?
The question is whether you're still assuming D is of this type.
No. Oh yes. Oh, sorry. What I'm well, I'm at the moment I'm just doing a TFT argument, topological field theory argument, and so I am not assuming that they come from representations of VOA, and then you can plug in that information if you want. Okay. So, but it turns out you can't put such a topological surface defect between any C and D. There's a notion of bit equivalence, and so when do we call 2 modular fusion categories bit equivalent? So that was developed by Alexei Davidov, by Nitschis and Ostrich. So this is equivalent by definition, or one of the definitions is that C box, C, right, C, the reversed is the Drinfeld center of some spherical fusion category. Right? And then there's a work by Fuchs, Schweigert, and Valentino, who point out that in order for such an interface topological to exist, C and D do have to be bit equivalent, and the different interfaces are then labeled by M is an F module category. Right, so there's an algebraic description of this situation. Okay, and so there's sort of computations you can do with this TFT. And I want to say, how do I, out of that picture, vaguely extract the data, if I at least want to hint at this, of F and gamma. But are there questions up to here or comments?
If D is C, I can take F C.
I will indeed say that in a moment.
So if I'm understanding, in this situation, you wanted some kind of anomaly cancellation to happen. Is that accurate?
Okay. Maybe, no. But I'm saying you can't put any, so I mean, so in particular, right, and consequence of bit equivalence is that the topological central charge agrees. Right? That's a consequence. So that therefore the actual central charge would agree mod A.
That's what you see topologically.
So,
Let's do this later.
okay.
But more clear.
More questions or comments?
So for the surface defect, you are somehow assuming that you have this TFT description, but of course the pure problem of finding the correlators doesn't have anything to do with the TFT. It's nice to have it, but for the actual solution, you don't need it. Can you make sense of the surface defect without talking about the TFT description? Is there something purely two-dimensional?
Can I make sense of the surface defect in the 3D TFT without talking about the 3D TFT?
Well, I mean, yes, yeah, this is sort of my problem, that somehow it seems to be a notion that is tied to the solution strategy, but not so much to the problem itself, right? Is that...
You could say it that way. I would treat this as a perk. Having the ability to write things like that allows you to reason topologically. So there is a two-dimensional version where you would walk through string nets, and then sort of the string nets, maybe you can think of as line defects on these, but Christoph can maybe explain that more, but I cannot.
We can discuss this after the talk.
More questions or comments? So, and so I want to say, so therefore,
Just a comment that with the gluons, you better ask to be multi-fusion.
what do you want to be multi-fusion?
F.
I wanted, I don't have to, right? I mean, I can always find an actual fusion, which does that.
Yes.
But it could be multi-fusion, and that would correspond to having a non-elementary.
Right, and then you can absorb M into F. So you don't.
Then I
you don't
can
need
absorb
separate. You
M
don't need
into
to. Yeah.
F. Okay, that you can explain to me afterwards. Good. Yeah. So if this picture is correct, it should be possible. If somebody hands me such a module category or such a surface defect, I should be able to produce these two pieces of data. And okay, so the so what's F going to be? And so F you get as follows. So what F will be is basically if you label these by two objects U and V, then there's a vector space of these point junctions, and that tells you the multiplicity with which U and V appear in the state space. But I want to say that in a slightly more complicated way. So I can apply the TFT Z to a two-sphere S2, which is decorated as follows. Up here, I've got a marked point, say X. Down here, I've got a marked point Y. I've got a line drawn on the equator, which I decorate M. So what I'm doing for you is I'm cutting out a sphere around this alpha, and I'm asking what does the boundary of that sphere look like? And this surface is decorated by C, and that surface is decorated by D. So that's an object in this sort of extended by decoration, the stratification sportism category. So to this, the TFT will assign a vector space. So I want to think of this as a functor from C box be, I don't, just as categories, so reverse, not reverse doesn't really matter. Let me put reversed. And I want to think of this as a functor to vect, which sends xy to this vector space. Okay, and this is actually contravariant, never mind. So I have a functor from here to vect, and because everything is finite and even semi-simple, this functor is representable, and that's the representing object. So if I call this functor f, maybe fm, then I'm saying that fm is equivalent as a functor tom in C box D reversed of nothing into this object fm. So that defines that defines the space of fields. That's how you get the space of fields out of the TFT. And then the gamma m is just this. That implies. Gamma sigma. Gamma m sigma. This. And then I claim this pair again provides it with a solution to writes it with a consistent system of correlators.
Do you assume M to be semi-simple?
Everything semi-simple.
Huh?
Yeah.
So it's not just any model category, otherwise.
Indecomposable.
So it's a joint algebra.
Well,
Isn't,
because we're not.
A joint algebra, yeah, it's same.
But
but it's
in
different now. It's
F, not in-
CNC.
Huh? But no, but in Z of F,
in F.
M, there is a joint algebra in Z of F.
uh,
Under this equivalence, it will be algebra in Z of F, and it's a joint
That of
Yeah.
yeah, full
to M.
set of
Yeah,
that.
it's the same.
That sounds right. How much on time? Okay, maybe 10 minutes. Come on, let's look at it. So I want to look. So that's okay. I wanted to state. So I want to now go to the boundary case, but let me maybe in words say one theorem. So or in words and just a few. Not giving all the details. So if we are back in the case where C is equal to D, and you can always sort of do this by going to some common modular category which somehow contains these two in a certain sense. So if you are in the case C is D, then you can show that all solutions, so all consistent systems of correlators, for which the vacuum, so 1 box 1, sits in F with multiplicity 1, which produces for you non-degenerate 2-point correlators. All of these solutions with these two properties come out of that construction. So these are in 1-to-1 correspondence to these surface defects, and therefore to module categories. So if C is equal to D, as Azad said, I can choose F to be C, and so these are therefore 1-to-1 correspondence to C module categories. So I'm saying this to say that this construction, at least in this case, where C is equal to D, we can show this construction to be complete.
To be exact, semi-simple.
Well, semi-simple.
But if you start with non-semi-simple module category
That's very
over fusion, can you do something still?
So that's what
C is semi-simple, but M is not.
C is semi-simple, but M is
C is modular fusion, but M is not.
yeah, then I don't know what to do. I can get, so here, well, we can discuss examples of this, but I don't know what to do with them. So the question of what if the input category, the modular fusion category, is actually not fusion, but just tensor, that's something that Aaron Hofer is working on.
You can write also gamma because you just want F.
Gamma.
Gamma is what? Yeah.
I find some boundaries. Boundaries. we also want to do conformal field theory, which have a conformal boundary condition, so one-dimensional conformal boundary. And so then the construction gets modified a little. So if our, so I just do the topological bit. So if our surface now has a non-empty boundary, so let's say it's a disk, then if I do the orientation double, then I want to not leave the surface like this, but instead I want to glue it together over the boundary so that I get the topological analog of the Schottky double over complex surface with non-empty boundary. And so what I do is I identify x and sigma with x and x on the boundary of sigma with x in the boundary of minus sigma, the same point, just orientation reversal, right? And so I have another copy of the disk and I glue together points along the boundary. So what this gives me is that in my example, I just get a two-sphere where the original boundary is now maybe an equator of that two-sphere. So that's my double. And I can again write, so for the construction in the presence of boundaries to make sense, I need C equals to D. I think this can be weakened, but that's not known for the moment how to do that exactly. But for C equals to D, what I will tell now works. So the new connecting manifold is again, you take sigma times an interval. So let's do our disk example again. Here's our disk. Then I take this times the interval minus 1, 1. So maybe here is t is 1, here is t is minus 1, and here is t is 0. And again, I divide out the relation. And the relation is that if this I call t, that for x in the boundary, I identify xt with x minus t. So over the boundary, I'm identifying points like this. Right, so you can now stare at this a little bit, and then you see what this becomes is a 3-ball. Then these boundaries are identified, right? So on the boundary, we do indeed get the double of the surface with the boundary glued together, and then in here hovering is a little disk, which is the remnant of this disk of the worldsheet, which set at t equals to 0. Right, and so if you look at this picture, it tells you how you can treat in this language correlators which have boundary components. You would say, well, this should be my surface defect. Now with the same TFT on either side, because you can walk around it. And if you've got the bulk field, well, the treatment is as before. Would be characterized by some topological point junction here on the surface. Boundary conditions are now boundary conditions to the surface defect. So I don't know, boundary to surface defect. So the different conformal boundary conditions, which are transparent to the entire VOA, are labeled by possible line defects which bound the surface defect. In this language up here, these will be precisely elements of objects in the module category F. And then boundary fields would sit on the image of these two boundaries where they're glued together. And there would be a ribbon which stretches into the interior. And then there's again some coupling here. And so you can ask how many boundary fields in some representation U are there? Well, you would have to sort of take this element M, which lives in the module category, and you act on it with U. And I don't know if there are different boundary conditions, like here is M and here is N, then maybe it's, I don't know if this goes into N. So you ask. So the multiplicity space is then given by a home space in the module. So that's the crash course on how to include boundaries. And until I'm stopped, I will go through this procedure in the easing example.
While we are cleaning the blackboard, can I make a comment? So if you look at the couplings of the bound field, of the bulk fields and the defect, you can read up of the multiplicities of the bulk fields. And this way you get information on the central algebra in the Trinfeld Center, on which Alexei Davidov will probably speak next week. Sorry? Sorry?
The title is locked in.
Well, you can always decide to override it.
Okay, easy. So I want to do an example where I have a disk. I've got a bulk spin, and I've got on the boundary, I've got two sigmas. This is possible if these correspond with changing fields, the Ising model. And so let's say out here, I have the boundary condition labeled by epsilon, which is minus, and here I have the boundary condition labeled by sigma, which is 3. And now I want to write this. I want to compute the coefficient which goes in front of the conformal block, which describes this correlator. So I go and I work out the TFT representation of this. So we have learned how to do this. We should find first a module category for the Ising modular fusion category. Well, there is only one semi-simple indecomposable one, which is Ising itself. That's the transparent surface defect. So we can just forget that from the start. And so there's only the diagonal solution, which we already discussed. So I get sort of 2 pre-images of that point and 1 pre-image for every boundary point. Then I'm asked to draw a ribbon which connects the 2 images here. Then I'm asked to insert maybe, so there's the surface defect which sits here, but it's invisible, but its boundary is not. And so one valid boundary for the invisible surface defect is any ribbon in the 3D theory. And so I want to, however, have different sections. So there's a part of this ribbon labeled by epsilon and a part by sigma. Well, that doesn't make sense, but it does make sense once I sort of add these lines which come in from the boundary. So this is also sigma, and this is sigma, and that's a one-dimensional home space from sigma into epsilon. So that's at least allowed, and this one is also allowed. So that's the 3-dimensional TFT presentation of that correlator. Now I want to understand, well, which conformal block is this? So you have to write your favorite conformal block for, so this is going to be a 4-point block already, at least that we can count. It's going to be a conformal 4-point block. And so our favorite conformal 4-point block, I have to do this picture again, we have an explicit identification of the boundary with some complex plane. This may be where I have a point at 0 and a point somewhere, say infinity. And then I get these 2 reflected points which sit at Z and Z bar, which would be these 2 points. And I have to maybe make some decision on how I would reach these 2 from continuum from my standard block. And then my standard block would maybe look like this. So, and so this would be alpha, and this is all sigma. Right, so that would be my standard block. And I want to expand this in a linear combination of those. So the TFT question I have to answer is, what do I have to write here? Some alpha, some coefficient alpha, so that that vector is the same as that vector. And so you can again evaluate these coefficients as a ribbon graph. And I claim the ribbon graph you get in this instance looks a little bit like this, and I will not compute the number for you. That's going to be an exercise. Okay, so I write a closed ribbon graph. And so this is alpha. I hope I got all the conventions right. So this is all sigma. And then this is the boundary circle. So there's a bit epsilon and a bit sigma. So that's just a ribbon graph from empty to empty. So that's a number. And I claim that number is the thing you have to put here to make that an identity. So this is the coefficient which goes in front of the conformal block. in order for this sum of conformal blocks to describe this specific correlator. That's how the formula is. I stop. Thank you very much.
So before thanking Ingo for these nice lectures, should I interpret the volume of the applause that it would be a good idea if Ingo writes up lecture notes, or at least distributes the handwritten notes, which I know in Ingo's case are almost as good as printed lecture notes.
Yes, please.
I can try.
Yeah, and we can also have them on the web page, just restricted to participants. Yeah,
Okay.
yeah. So I think that would be very helpful.
Yes,
Yeah,
yes,
yeah. But
please.
okay, this was the reaction I wanted to have. Thanks, Raoul. And
Remember all your names.
but Ingo, you should have the option to have assistance for writing up the lecture notes. So. Okay.
Don't point out.
Anyhow, we have time for questions. Then we had lots of questions, I think. Yeah.
If clarification, you mentioned before concerning my questions before. So if I give you in a sphere some points and a conformal structure, therefore you colored by modules for a VOA, you know how to write down a function which is it transgroup invariant or is it multi-valued and mapping transgroup acts on the branches of the values?
So the mapping class group dependence is captured by the three manifold which is glued to it. The whole object together is invariant, but not just the function. And the function will have a monodromy, but that monodromy is what you would have wanted to assign to the new configuration because you've also deformed the three manifold which attaches to it. So in this example here, right?
So strictly speaking, if I only give you the sphere and the points with the colors, etc., you don't have a single valid function. But if I give you the ball with the topological decoration, then you have a single valid function.
What single valued means has changed, right? So in this picture, right, clearly, if I take this point and I continue it around here, I've got a different value, but I'm not surprised because the picture
ball is
inside has changed.
Yes, I get it.
Could you give an idea? You formulated the theorem that all solutions are in bijection with semi-simple module categories or exact module categories?
Well,
at which point?
Theorem exists for modular fusion category C equals to D, both modular fusion. And I require that the field space has vacuum with multiplicity 1, and then I get the correspondence to indecomposable semi-simple module categories over the modular fusion.
No, but semi-simple exact ones. Where at which point you use exactness?
It's all semi-simple. I don't.
Yeah. But exactness means semi-simple. Yes. At which point it's important semi-simplicity of module category.
It's probably hard to say because you see an object, you write it as a sum of irreducibles.
It's imposed by topological theory because you have this.
Can I give a quick answer? You want the algebra of bulk fields to be a Frobenius algebra.
Yes, but Frobenius doesn't need to be simple.
Well, for this, it has to be a pivotal module category. A pivotal module category is exact. And exact module categories over fusion categories are semi-simple.
So pivotal implies exact here.
Pivotal implies exact.
Oh, really? Okay. Okay.
Because pivotal is defined in terms of relative Serre functors, and the existence of relative Serre functors means exactness.
Okay.
Isn't there this work of Shimizu where he extends it to the non-exact setting, where he only defines them first on just
well, these are relative Serre functors which are only partially defined. They're only defined on subcategories, which is very natural to do because also ordinary Serre functors are defined on projectives to injectives. Yeah.
But he somehow extends them. He calls them quasi-Frobenius.
But then you don't get really symmetric Frobenius algebras.
You need symmetric also.
Okay, I think 2 announcements before thanking Ingo. Let's please go to the photo. And there was a misprint in the announcement for the afternoon. So Bernardo's talk is at 2:30. Of course, this was the idea of moving things. So please come to the talk at 2:30. 3:30 will be too late, but let's think Ingo again. No, this is.
Up to the point